In this video, we're going to talk about the binomial theorem and Pascal's triangle. These are two sort of applications of combinations. The binomial theorem specifically, and Pascal's triangle is a very cool relation to the binomial theorem and combinations. So sometimes we have polynomials that, when expanded, can be a little bit difficult to do step by step. So we have this really cool binomial theorem that sort of does it for us. And it says that if n is a positive integer, then x plus y raised to the n is going to be n choose 0 times x to the n, plus n choose 1 times x to the n minus 1 times y1, plus dot 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 all the way up to n choose n of x to the 0 times y to the n. Now we have this really convenient notation for this. And this is the summation notation, that basically you put I equals 0 into the first case, and you solve for that. So in the first example, if we have I equals 0, we get n choose 0 times x to the n minus 0 times y to the 0, and then we add the next value of I, so then we add 1 to I, so I is now 1, and we go n choose 1 times x to the n minus 1, y to the 1, and then we keep going until I reaches n, and you'll see that this is exactly what I wrote up here, just expanded out. So this is a very convenient summation notation. Basically, you start with the largest power of n, and then each subsequent addition, you just move one power of x to the n over to the y until y then reaches y to the power of n, in a nice informal manner of explaining what's going on here. So let's put it to use. Let's do it the way we know, with x plus y raised to the power 2. Of course, we know this is the same thing as x plus y times x plus y, and we can just FOIL this out to be x squared plus x times y plus x times y plus y squared, which is the same thing as x squared plus 2xy plus y squared. Now let's do the same thing using the binomial theorem. So first, we're going to have 2 choose 0 times x to the 2 y to the 0 plus 2 choose 1 x to the 1 y to the 1 plus 2 choose 2 x to the 0 y squared. So now 2 choose 0 is going to be, I'm going to write this on the side, we're going to do all three at once. 2 choose 0 is 2 factorial over 0 factorial times 2 factorial, which is just going to be 1. 2 choose 1 is 2 factorial over 1 factorial times 1 factorial, which is 2, and 2 choose 2 is going to be 2 factorial over 0 factorial times 2 factorial, which is 1. So let's plug those values in. We're going to have 1 times x squared. Y to the 0 is just 1, so we'll just leave it out. Then we're going to add 2 times xy plus 1 times y squared. And this happens to be the same thing we got up top. So the formula works for a small power, and you can check this for a higher power if you have any questions about that, or have any concerns about whether this is true or not. But take my word for it, it is true. And I also want to direct you to another cool thing that we see here, and that is 2 choose 0 and 2 choose 2 have the exact same formula. So here's an interesting thing. I'll write this as a cool aside for things you can do with combinations. N choose k is the same thing as n choose n minus k. So you can use these interchangeably. As an example, 49 choose 6 is the same thing as 49 choose 43. So there's a cool little thing, and we're going to see a nice friendly application of this very shortly. But first, one more practice problem. And I do this because sometimes when you just say, oh, x, y, they both have constant 1 in front of them, so it's not that difficult. But what is 2a minus b raised to the 4? So I'm going to do this really sort of quick and point out the important things here. So our first one is going to be 4 choose 0. In fact, I'm going to add them all vertically, just easy visually. So we're going to have 4 choose 0 all the way up to 4 choose 4. Our first one is going to be 2a to the 4 times minus b to the 0. And then we're going to have 2a cubed minus b to the 1, 2a squared minus b squared, 2a to the 1 minus b cubed, and 2a to the 0 minus b to the 4. I wrote it vertically like this so you could see the progression of step by step what's happening. The power for 2a is decreasing and the power for negative b is increasing. So the interesting thing here to note is that we take this whole 2a and this whole minus b and we stick it into the thing that's getting raised to the power. We basically say x is equal to 2a and y is equal to negative b, and then we plug it into the formula. So the important part here is that you remember to put the 2 with the thing that's getting raised to the power of 4, 3, or 2, or 1, because that will change the result if you forget to do that. So we could leave it like this, and it would be fine. However, I will simplify it a little bit. So 4 choose 0 is going to be 1. So we're going to have 1 times 2a to the 4 is going to be 16a to the 4, plus 4 choose 1 is going to be 4 times 8a cubed, but we have negative b, so this is actually going to be subtracting 4 times 8a cubed. Then we will add 4 choose 2, which is going to be 4 factorial over 2 factorial times 2 factorial, which is going to be 6 times 4a squared times b. Our next one is going to be minus 4 times 2a times b cubed. This should be b squared in the second one. And the first one should be times b. I don't know why I keep forgetting to write the b's. I'm doing the subtraction right, but I'm forgetting the b's. And then we're going to add 1 times b. So when we simplify this, we're going to get 16a to the 4th minus 32a cubed b plus 24a squared b squared minus 8ab cubed plus b to the 4th. So that will be our end result there. There should not be any mistakes there. I know I sort of made mistakes by forgetting what to write in as we were going along, but as long as you recognize the pattern, you should be able to see very easily that, hey, my powers are wrong. And now you have a nice simple way to solve these problems. There's something very cool, though, that relates to this sort of 4 choose 0 through 4 choose 4 thing. And that is called Pascal's triangle. So here's a little cool thing. If we label the triangle here, and we start with 0 choose 0, and then the next line we write 1 choose 0 through 1 choose 1, and then we just keep increasing our n as we go down, and then we go through all of the k values from 0 to 3. Then we get something interesting here. We get a 1 we get a 1, another 1. For 1 choose 0 is 1, 1 choose 1 is 1. 2 choose 0 is 1. 2 choose 2 will be 1. Now what is 2 choose 2, or 2 choose 1? Well, there's two ways to do that. And what's cool here is if we add the two upper diagonal entries together, we will get that result. So 3 choose 0 is 1. Now what does 3 choose 1? Well, if we add the 1 and the 2 together, we get a 3. So what does 3 choose 2? Well, we saw that 3 choose 1 is the same thing as 3 choose 2, which makes sense now because of this cool little Pascal's triangle we have here. And then of course the outsides will always be 1. So we have this claim here that n plus 1 choose k is n choose k plus n choose k minus 1. Which means if we take this 3 choose 2, so we're going to write this as 2 plus 1 choose 2, this should be the same as 2 choose 2 plus 2 choose 1, which we see is actually the same thing as what we have in this triangle right here. So that's a cool claim, and it turns out that if you break apart the formulas and find an equivalent formula between the two, this holds. So when I went back into this previous problem and I found these numbers right here, you'll notice that after I found this 4 right here, it didn't take too long to figure out what the next value was. And that was because I was able to figure out the numbers for the triangle at that line. Because if we go next, we know our outers are going to be 1, then we have 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. So of course this is x plus y to the 0, to the 1, to the 2, to the 3, to the 4 here. So I want this line when we deal with something to the 4. 1, 4, 6, 4, 1 are the coefficients, and they just so happen to be 1, 4, 6, 4, 1 here. So that is a very cool trick to help you figure out the coefficients in a much faster manner. So here, as another quick example before we go off, we have x plus y squared is x squared plus 2xy plus y squared, which is very easy to see is the third line in the table. So what I should say formally is that x plus y to the n takes coefficients of row n plus 1. So this is row 0, this is row 1, this is row 2. Oh, sorry. This is row 1, this is row 2, this is row 3, this is row 4. So x plus y to the 2 takes row 3. So here's a question. What are the coefficients of x plus y to the 6? Well, we just draw the triangle. So we can actually do this very, very quick. In fact, we have to go up to the 7th line here, so we can do that very, very quickly. So this is the 1st, 2nd, 3rd, 4th, 5th, 6th. We just have to go one more line, and we will be done. So if we just add up all of the preceding two numbers here, so to get 15, for example, we took 5 plus 10 to get 20. We took 10 plus 10 to get 15. We did 10 plus 5. And this is the coefficients of x plus y to the 6th. It'll be 1 x to the 6th plus 6 xy to the 5 plus 15, x 5 times y plus 15 x to the 4th y squared plus 20 x cubed y cubed plus 15 x squared y to the 4 plus 6x y to the 5 plus y to the 6th. And this is your result. And I could do this that quickly just from Pascal's triangle. So that is really cool. 1, you find the row. 2, you remember the pattern for your powers, where x starts at the highest and goes down 1 each addition, and y starts at 0 and goes up 1 each addition until you've filled out that row for the triangle. So that is something very cool you can do, and before I go, I am going to ask you to do this on your own. X plus y to the 8. I won't solve it for you, but have a go at it, see if you can do it. It should be really simple. In fact, if you can remember this, x plus y to the 8, I will even go back to this triangle here, and you just need to extend it 2 rows, figure out the pattern, and see what's going on. So that was the binomial theorem and Pascal's triangle. If you have any questions on these things, feel free to leave them in the comments, and I will get to them as quickly as possible and hopefully clarify any questions you have.